Thank you. We start by thanking Vishnu and the other organizers of the workshop for inviting me to such a wonderful place and giving me the opportunity to talk about my work. So today I will talk about, I will introduce a multi-partite entanglement measure, and I will also construct its holographic role. So this will be on the lines of how we understand entanglement from holography using the entanglement formula. But instead of measuring the bipartite entanglement entropy, I will introduce a measure that probes multi-partite entanglement states. So this is work done in collaboration with my student, Rakshu Sharma and Vinit Krishna. Rakshu is on the market this year, so please keep them. They're both very good. Okay, so let me just say a few motivational words about multi-partite entanglement. So in recent times, ideas related to quantum information, such as entanglement entropy or quantum error correction, have been quite effective in learning about nature of holographic states as well as the encoding of the bulk into the boundary. In other words, developing a finer understanding of the radius CFT correspondence. So we expect that if we also understand multi-partite nature of the entanglement of holographic states, we would have even finer understanding of this correspondence. So with this in mind, we wanted to construct an entanglement measure which probes multi-partite entanglement, and we would like to have it to have certain nice properties, which I will clarify in the talk later on. So before I say what I mean by nice properties, let me first start by defining what I mean by entanglement measure in general. So this discussion starts with having a Hilbert space, which is a tensor product of a bunch of Hilbert spaces. And if there's a state psi that belongs to this Hilbert space, which has this tensor product factorization, then one can talk about entanglement of this state psi. And what do I mean by that? So in order to make it clear, let me write this explicitly in terms of a wave function. So I pick a basis on these individual Hilbert spaces and explicitly write this. So this is nothing but expressing this state in terms of some arbitrarily chosen basis vectors of H1, H2, H3, H4. So I hope this expression is clear. Now, a general state would have this form, and not necessarily just the product form, where you have a state from here, direct product with a state from here, and so on. And the entanglement, roughly speaking, is a measure of how much it is not of the product form. How much of the sum do you need here? So we will make this notion precise by introducing these measures. So what I mean by these measures is that is all the information in the state that is invariant under local unitary transformations. Okay, so with this criteria, I characterize all the entanglement that is present in the state. So you have this wave function psi I1, I2, I3, and correspondingly you will have the wave function corresponding to the bra, which is just a complex conjugate of this wave function. And the idea is to construct quantities out of psi and psi bar that are invariant under local unitary transformation. By local unitary transformations, I mean the unitary transformations that act individually on H1, H2, H3, H4. So in other words, U is of the form U1, tensor U2, tensor U3, blah, blah, blah. So all the quantities that we can construct out of psi and psi bar that are invariant under such a U is what I'm calling an entanglement measure of the state psi.
So don't you need more? You need, I guess you'll demand it should vanish for a separable state. It should be 0 for a separable state.
So the separable state will take us into whole different.
I see. For a product state, it should be 0 in your case.
Yeah.
And
it need not be. If it is, you can make it 0 by suitably subtracting certain quantities. But this is what I mean.
I see.
This will not be a necessary condition.
Don't you also need that it should be monotonic under LOCC?
No.
But that's necessary.
This is what is called the LU criteria, local unity criteria. But
I see. But if you say entanglement, don't you physically want that, like something which is invariant under that can only decrease under local operations in classical domain?
you may require that. That would be further, characterization of the state, and give you a smaller set of measures. But for now, I'm just considering the general measures. So what these general measures do is basically they have the property that they do not change if observer controlling H1, H2, H3, individual observers controlling H1, H2, they do something to their Hilbert space in their own labs. This particular quantity will not change. So that for me is what I'm calling an entanglement.
If they couple their system to something in their lab, it should not be this quantity increases. Then it would be.
Well, that's what I'm saying. So this is something that you can add as a characterization, but
okay.
For now I'm not doing that. Okay. All right. So let me, in this framework, describe. So how would we do this? We want, as I said, we are taking this psi and psi bar. We are making quantities that are invariant under local unitaries. So that is easy. Basically, you take a bunch of psi's, a bunch of psi bars, and you contract indices. Okay. So this I1 is a fundamental index with respect to U1, and this I1 here is an anti-fundamental index with respect to U1, and similarly for all the other indices. So if you want to construct an invariant, you simply want to contract all the indices. So in the bipartite case, this is easy to see. We can take psi I1, I2. Now if we just take just one copy of psi, the other only one copy of psi bar. First of all, if you want to contract the indices, the number of psi's and number of psi bars should match. And if you take one of each, then you simply end up constructing the normal state. But you can do, you can construct more complicated quantities by having multiple psi's and multiple psi bars. So at this stage, it is convenient to introduce some sort of a notation. So psi I1, I2, let us denote this by a vertex here, psi, with two types of arrows coming out. This arrow is for the first party, and this arrow is for the second party. Okay, I point the arrows to be outwards because both of them are fundamental indices. And psi bar would then be bivalent vertex with two arrows going in, I1 and I2.
So psi was the matrix on top. So psi I1, I2, I had three indices in the beginning.
No, this is dot dot dot. So here I'm not specializing to any case.
Some of the indices are a little on the microscopic side.
Yes, it's
Okay, I will try to write it.
But now it does have three indices. No, I1, I2, I3. So So IN, But
IQ, so this would be IQ. So in general, it starts with Q parties. Right? This definition was for general number of parties, namely Q. But for now, I'm just specializing to Q equal to 2.
Oh, I see. Now you're talking about Q.
Okay. And then I will generalize again to higher Qs. The generalization to higher Qs will be straight. I will work with Q equal to 3, but you will be able to see what I mean for Q equal to 4 and so on. So now the measures that you can construct are basically, you take a bunch of psi's, okay, and the number of psi's you take is n. This I call the replica number. And you take the same number of psi bars, and you simply contract all the indices. The solid line goes with the solid line. So remember there are arrows here. So the outgoing arrows need to go in into this vertex. This would be, this row is of psi bars and this row is of psi. So you simply want to contract, join the solid arrow with the solid arrow, say like this, and the wiggly line with the wiggly line. So it would be something like that. Okay. Now, written this way, this may look complicated, but because these vertices are simply bivalent, what you're going to get are nothing but a bunch of necklaces. Okay, so you will get a generally disconnected graph where each connected component would be a necklace of which would look like this. Okay. I hope this is clear. And these are nothing but the Renyi entropies. This is what we call trace row to the end. I mean, Renyi entropy would be the log of that and divided by 1 minus n. But normally speaking, this is the measure that gives you the Renyi entropies. And defined this way, you would get in general the product of such quantities. Now, at this stage, we can introduce another notation, a notation for the density matrix rather than psi and psi bar. It would look the same. I could have used colors, but I would end up wasting some time, so I didn't use colors. But so what I mean by this graphical notation for the density matrix is the following.
In Q equal to 2, psi is the density matrix. In the Q equal to 2 case, psi is the density matrix.
No, psi is a wave function.
There's a psi, I1, I2 and times the basis.
I1
it's a wave function. I see. So
I1 is the fundamental index of first and first space. I2 is the fundamental index.
So I'm a little confused about, let's say you wanted to write rho square.
Yes.
You need psi and psi bar.
Psi bar.
Where is the psi bar in that notation? All the blocks look the same.
Yes. Psi bar is the top row.
Is the what?
Is the top row. Is the top row.
No, in that necklace.
Oh, in the necklace, yeah, sure. So as I said, maybe my notation was a bit messed up here. I should have these arrows I didn't draw properly. So the psi has 2 arrows going out,
Right.
and the psi bar has 2 arrows. So it's always psi bar.
So between the dark blobs there is a psi bar sitting which is invisible from the no.
Okay, so here for example, this would be psi, this would be psi bar, this would be psi.
Very good. So it's alternating psi bar. So
Alternating psi,
alternate blobs are of different kinds. So one of them is circle.
Yeah, so let me do this. Okay. So now let me introduce the notation for the density matrix. Rho I1 J1 as trace of as sum over I2 psi I1 I2 psi bar J1 I2. Okay, so what I've done here is I just traced out party 2. Okay. And I have open indices for 2 open indices for party 1. Okay. So in terms of this notation, I have this party 1 leg with the arrow going out and this arrow going out. Okay, so this is I1, I2 and J2. This is clear. And usually what we do to denote psi is we just not make explicit this 2 second party because we have traced this out. So we introduce this bigger block and call this the density matrix. So the density matrix here is just this. Okay. So far I'm not saying anything new. I'm just introducing graphical notation which would help me talk about the multi-partite stuff easily. Okay. So this is just the density matrix, and then that necklace that I drew was just the necklace of these 4 blocks. Like that. And then I can put the arrows only one clockwise way. And this would be trace totally 4. Okay. So here I just mentioned how this particular point of view of just taking a bunch of size and a bunch of sidebars and contracting indices appropriately just produces something that we know and we are familiar with, namely the range entropies. So we cannot get more than that in the bipartite case. We have a state of 2 parties. These are all the entanglement measures defined previously that you have here. Now, one observation in this is that even though we write usually the range entropy in this way, trace wrote there, it is symmetric in both the parties. This notation obscures it, but if you go back to this notation here, it is clear that it's symmetric in both the parties. I could have traced out party 1 and done this construction with party 2, and I would have obtained the same measure. This would just mean that I'm hiding the solid line and making manifest the V line, and I would draw a similar diagram, but it would end up being the same measure. So the manifest symmetry between the 2 parties is hidden by this use of density matrix, rather than keeping explicit sign sidebars. Another thing to comment here is that even though we have these measures, the measure that we like for the bipartite case more than the others is the one Neumann entropy. And that is limit n going to 1 of 1 minus n log trace to n. Okay.
Can I just ask a few clarifying questions? One is, are you in any state or is it a vacuum state?
No, any state.
Any state.
Yeah, this discussion is for
And then,
state.
is it really entanglement? Because now you're saying that for Neumann entropy is what you're interested in, or at least one of our favorites, but I thought that for entanglement measure, what I was interested in was actually the mutual information.
Which pure state. That's
Oh,
what you said at the beginning. So it's
So it was pure states.
Yeah,
The total system is pure.
yeah.
Okay, so that's so.
No,
so
but
entropy
mutual
is-
information also you can think of it as a particular combination of one Neumann entropies.
Fair enough, but the total the key difference is that the total information is 0.
I mean, if you had mixed states, then what for Neumann entropy would give you a notion of how mixed the state was, not of entanglement. Right?
That was just one.
If you wanted entanglement, then you would have to look at distance to the nearest separable state, which, as you said, you don't want to do.
I mean, I do not want to
I know,
use
I
the
know.
word separable. I don't know whether you know besides that. I mean, the separability is something very delicate thing, right?
It's just that you can write the density matrix as a sum of positive.
Yeah, exactly. It's about convexity.
Right.
It's not about entanglement.
Entanglement is usually defined as that way.
Yes, but okay, fine. I mean, let me just, maybe we can talk a little bit more about that. But for now, I'm just considering pure state. So let me just stop at that. Okay. So for pure states, this is what I mean by entanglement. Now, if you have a mixed state, you can ask whether a given mixed state, given density matrix, separable or not separable, and all these questions. But these are not the questions I want to get into today.
Abhijit, can I reformulate relative entropy like this in some way?
Relative entropy, no, here I'm just working with a particular pure state, as I said, not quite two density matrix. Okay, fine. Okay, so why do we like this particular, n equal to 1 version of the range entropy is more than the other? Well, there are a couple of reasons. One is a reason that comes from, just because it's so closely related to information, Shannon entropy, and issues of physical resources. So in that sense, one Neumann entropy is a very physical quantity that you might want to look at. But as string theorists or people thinking about holography, another reason we would like one Neumann entropy is because the dual of one Neumann entropy is given by the Rutherford formula, which says that you simply compute the area of the minimal surface that extends to the bulk. Now the Renyi entropies also have a similar type of description, except that the stuff that extends into the bulk is heavy and back reacts on the geometry. So in that sense, what makes this different is that the tension of the minimal area surface is vanishingly small. It does not back react on the geometry, and it becomes a probe measure for holography. Okay. So this is a nice distinguishing property of this one-level entropy compared to other ends. Now for multi-partite entropy, multi-partite entanglement, as you will see, there is really a zoo of entanglement measures that you can define. So you need some sort of a guiding principle to arrive at a quantity that you like. Now one guiding principle could have been coming from quantum information, but I don't know of any systematic studies of multi-partite entanglement from that point of view. So as string theorists, we will stick to this particular guiding principle, that the measure that I want is the one that has a nice probe bulk description. Okay, so with that in mind, I will try to characterize the multi-partite entanglement measures. Okay.
Abhijit,
Yes.
is there a way to formulate this in the CFT? This kind of multiple?
Yeah, sure. I will say
That's in the CFT.
afterwards. So far the discussion is quite general for general states, but in CFT we can think about it from a path integral point of view. In terms of replicated manifold or even with the twist operators.
But this bond number entropy is somewhat singular from the CFT point of view, right? You take some limit equals to 1.
Why is it singular?
The sense that you have to compute it for n and then take analytic quantity.
It's singular that all the Renyi entropy is also singular. Just because of UV divergences. UV
Oh, you're talking the UV divergence.
No. I mean, you cannot directly compute without taking.
No, so that is correct. But I don't call it singular.
It is singular in the sense that you have to first compute it for all n and then take the limit.
Yeah, you have to find an analytic expression and then continue that expression to 1.
Yeah. So
There's no singularity in this process.
no singularity. And made by singular.
Okay, great.
I mean, it's somewhat special.
Yes, I agree with that.
Especially from the point of view of the replica trick, not otherwise.
Yes. So, although from the gravitational point of view, it is simple.
Okay, so now let's look at let's say q equal to 3. I will not do q equal to 3, q equal to 4. From this it will be clear what I mean by general q. This is just to be complete. So now I want various measures that give me a multi-partite entanglement, because now my state lives in the tensor product of 3 factors rather than 2 factors. So again the same story, you have a bunch of size. I will not draw the arrows. I think it should be clear. So these are this is the notation for the index of party 1, the index of party 2, the index of party 3. So I'm just taking a bunch of them. And now you can join these indices so as to form a local unitary invariant. And you can do this in a bunch of ways. One possibility is this one. Okay, so what I've done here is I've connected the solid line and the wiggly line always in the same fashion. So the solid line and the wiggly line goes to solid line and wiggly line. This guy, the same here, the same here. In other words, I'm not distinguishing the solid line and the wiggly line. In other words, what I'm representing here is basically a bipartite measure where the party 1 and 2 are treated as a combined party, 1, 2. And this guy, party 3, is the one that does different things. Okay? So in that sense, the definition that I gave also includes less partite entanglement measures, But this is not what I will be interested in. We don't want measures where two lines are treated in the same fashion, because those would give us one less party entanglement. So the kind of measures that we want where all the lines do different things. So one possibility is like this. Okay, so this is just an example of kind of measure that we can consider. So this is indeed genuinely tripartite in that no two parties are treated in an equal footing. Okay, and so more abstractly, the way the measure is specified is by specifying permutation elements. So now, because let's first consider the party 1. I need to take these guys and I need to contract it with these guys. So if I specify a permutation element, sigma 1, associated to the first party, which is valued in Sn, where n are the number of replicas here, then this specifies how this glues, how the solid line goes to the upper set of solid lines. And similarly, sigma 2, that would be for the wiggly line, that would specify how the wiggly lines are connected, and then sigma 3 and so on. So in all, a measure is specified by specifying these permutation elements. So I now kind of generalize to Q. You specify Q permutation elements, and that would give you a measure. But this is a redundant description because you can permute the labels of these replicas here for size, and you can also permute the replica labels for these. So in other words, there is a freedom of left multiplication and right multiplication for these guys. Okay, so you can use, let's say, the left multiplication freedom to set one of these elements to 1. You can always do that. You can always set one of these without loss of generality. You can gauge fix one of these sigmas, let's say sigma for the first party to 1. Okay, and the other ones you can specify arbitrarily. Even this has a freedom under conjugation. Because what you can do is you can take these sets of this combined set and move this around, and you will still obtain the same measure. Okay, so this would give you a freedom, a gauge freedom of conjugation. Okay. Okay. Good.
Sorry, can you write this measure and just using more conventional? I mean,
Yeah, I will do that. So again, in the same way, let us construct the density matrix, using which we will have an easier time writing the measure. So the point that I'm making is that the multi-partite measures are given by these many, by this data. There are many such measures. So if the number of measures, the number of index contractions, they increase very fast as you increase n, faster than factorial. Okay, so the set of measures, unlike in the bipartite case, is huge. So you don't really know which one that you want. You have this huge row of measures. What will you do with it? How would you narrow down on the measure that you want? Namely, the one that is nice holographically. So what we have in mind is, in this huge zoo of measures, we want a family that is labeled by an integer, the way Renyi entropies were, and then we would like to take that integer to 1 to obtain a nice holographic measure. So this is going to be our thinking. Okay. So far I didn't give you an explicit measure, but now I will give you the measure that turns out to have nice holographic properties. So first let me define a density matrix on two parties. So again, Q equal to 3. So what I've done is I've traced out the third party. I'll write that explicitly. this has is a density matrix on party 1 and party 2. Okay, so you can think of this. So rho here is a map from H1 tensor H2 to H1 tensor H2. So the way this was just a map from H1 to H1, this is from two things. So it needs to have, if I denote it graphically, it needs to have two arrows going in and two arrows coming out. Okay, so this is party 1. So I hope this notation for the density matrix is clear. This is just a natural extension of this notation. Now let's get to the measure that we want. So a nice property of these Renyi measures was the following. When you have this kind of measure, which looks like a necklace, there is a symmetry. You know, if you rotate this, you will get the same measure. So this is called the replica symmetry. Zn replica symmetry. So we will look for measures which has symmetry of this sort. Okay, and it's clear what kind of measures would have that. So we will construct the following. So let me first write the rho in a rho to Vn in a suggestive way. So in this case, in the multi-partite case, raise rho to Vn. Let me write it like this. So I'm joining this point to this point, and this I have constructed rho 3. Okay, and this as a replica symmetry. So this is how I like to think of raise rho to Vn. Here it is just n equal to 3, but in general it would be just a bigger difference. So now the measure that turns out to have nice properties here is the following. This is clear. So each of these blobs represent a density matrix, and contracting the indices, not in a usual way we contract the indices of a matrix, but rather in a somewhat of a weird fashion, where we are making a square grid out of these density matrices. Okay, and now we also glue this edge back to this edge back to this edge back to this edge, and so on this side also. So the way we had a circle here, a circular lattice, here we have a toroidal lattice. Okay, and I also want the size of this lattice to be n by n. Both sides I want n and n. Okay, so this will give me a quantity that would be analogous to raised root n, and let me call this Zn. Okay, is this clear?
So, identifying the two periodicities is forced upon you by this probe.
Is supposed to?
Why do you identify the two periodicities? Is it because you want the probe?
Yes. So this is a requirement. It's a condition that you need for
probe.
Yeah.
Okay.
Exactly.
So in the event that rho is pure, what is this quantity?
Rho is pure.
I mean, so let's say rho has a form 1, 0, 0, 0. What is this quantity then? I mean, in the Renyi entropy case, we know what it is. It's just 1.
Rho is rank 1.
No, let's say rho can be put in the form 1 and 0s everywhere.
Yeah, rank 1 I can find.
So then what? That's a pure state, right?
Yeah,
It
that's
is
a pure state. So meaning the third, this had support only over one of these items, right?
So let's say once you reduce to over 3, and I'm just trying to get the intuition for the Zn. What would Zn be in that case?
Yeah.
If rho was pure.
So let's see. In that case, so okay, you can the way you can think of this is that you introduce this. You can restore the third index. Okay, and what you're saying is that let's assume that there is no, the third index is just 1. So there is no real connection between them.
Yeah.
So the way to resolve this is the following. This guy is simply okay, this is what I mean by this equation. If you see what this equation, this is exactly this equation. Okay. Okay. So now basically what you're saying is that there is nothing there. Right? There's no connection between them. So you just carry that out here. All these things are disconnected like this. Whatever it is.
That's a nice form. Like the Renyi entropies are just 1. I mean, depending on how you normalize them, all of them. They all
And
have
is
the
this
same
unique? How do you, it would seem as if you could cut them in 2 directions. So there's
This one is not
T and a
the.
U diagonal. Yes,
No,
it's
so,
T
so
diagonal.
okay, I need to be a little bit more careful here. So,
There's only one. The third one is peak, right? It's not. They're not being treated symmetrically. Because
Oh.
it's row 1, 2. And
Okay,
you-
right.
Third one
It's
is
a 5 cube theory with 3
with 3
distinct.
different peaks. Yeah.
no, the point is that this is another point that I was going to make. That it may look like the third party is not treated in the same fashion as the first two, but this measure is indeed symmetric in all the 3 parties.
I see.
The way that's why I emphasize this here. This rho, using rho, always obscures the symmetry of party 1 and party 2 here. In the same way, using the rho language obscures the symmetry here. But if you resolve and write these vertices explicitly as contraction of sine psi bar, you will start seeing a hexagonal lattice. And hexagonal lattice would have this symmetry under permutations of all the parties.
I see. But you're saying any case if it's pure, it's not like Zn takes a particularly simple form. It takes on
It
some.
may, I think it may, I have to do it, I mean, I cannot do it in my head.
Isn't it just the bipartite Renyi?
Yeah, it would probably be that. Yeah. I mean, I can tell you that I won't get into it.
So, Abhijit,
Yeah.
if you take a GC stage,
Yes.
what should be the answer for this mechanism?
Yes, I will.
Having this product.
But this, yeah.
Just to make sure that I follow, what was the requirement that fixed this invariance?
Yes.
So I'm not, I'm just giving you directly the solution.
Yeah, no, but
The guiding principle was that I want a measure that is given by a probe holographic quantity. A geometric quantity in the bulk that does not back react on the geometry. Just like the Ryu-Takahashi formula. The Ryu-Takahashi formula is just the area of a minimal surface in a given background. Right? I'm not talking about quantum corrections or anything, just at reading order. The entropy is given by just the area of minimal surface that you draw in the given background associated with the state. Okay. So that's the kind of measure I want. And this is to contrast with, let's say, Renyi entropies. The Renyi entropies are also a similar type of object, but now this minimal area surface is actually a heavy cosmic brane. And that will backreact in the geometry. So I want a measure that does not backreact in the geometry. And I'm just giving you a solution.
yeah.
Not yet, but this is a process. This is a step in that. Okay. So I hope this construction is clear. I will answer the question. Okay. So again, I mean, if you just the way this rho n had a replica symmetry, this also has a replica symmetry, and that is Zn times Zn. Because one Zn will permute these guys, and the other Zn will permute the columns, the rows and the columns. Okay. And now the generalization to even higher number of parties is clear. What I will do is that if I had q equal to 4, I will constrict rho on 3 parties, and that would have the rho vertex would look like this. This would be something that comes out of the board, and then this is a 3-dimensional vertex which I put together to form a 3-dimensional cubic lattice with periodic boundary conditions. And in that q equal to 4 case, that is what I will define as Zn. So here, if you wish, I can put 3 because this comes from 3 parties. When you have a cubic grid, that would be for 4 parties. So that would be Z4n. Okay. Okay. So once I have this quantity, I just do the following. I take limit n going to 1, 1 over 1 minus n, log Zn. Okay. So this formula is a little deceptive because the way I am defining the quantities are for integer n. So as I have pointed out, these quantities are inherently defined for integers, the way any entropies are. And then I am assuming that there exists an analytic continuation. It may or may not exist, but for states for which it does exist, I will take this limit. And I will define this quantity to be SQ. We call this quantity multi-entropy. For states where Zn is analytic in n, I will analytically continue Zn beyond integers and then take limit n going to 1, and the resulting quantity I am defining to be the multi-entropy. Okay? So this need for analytic continuation, or rather the prospect that it may not exist, was emphasized recently in a paper by Pendleton and collaborators.
So then don't you satisfy the conditions of Carlson's theorem? Because if you analytically continue n in the complex plane, this will not grow very fast, right? If the density matrix eigenvalues. So analytic continuation should exist.
Well, there's certain things. I mean, you have to. I can go into that if you want. So maybe let me just comment on that. So indeed, usually you could have asked this question here in the case of Remy entropies. Why is it that the replica trick is well defined there? Well, one thing is because there is a different formula for the von Neumann entropy. Namely, you just diagonalize the density matrix and use lambda minus lambda log lambda, and that uses it. You don't need any of this way of defining the von Neumann entropy. But here, this is the only way that it can be defined. That's one thing you need to be a little more careful about analytic continuity. It's defined through analytic continuity, no other way. Okay. But let's go back to, in what sense the analytic condition exists, or whether it's unique, and so on. So Carlson's theorem guarantees uniqueness. So it says the following. So the problem that we have, this is the n complex plane. The problem that we have is that we are given these, so what we call them as any multi-entropies at values n equal to 2, 3, 4, 5, and so on, let's say. And you are asked whether a complex function could exist. So Carlson's theorem says the following. If we have a function which is analytic in the right half plane and decays slower, does not grow faster than e to the pi y in the imaginary directions, and in these directions it behaves in some exponential way or some c, and then it vanishes on these integers, then the function must be identically 0. That's what the Carlson theorem says. You can use the Carlson theorem to show that the analytic continuation that you have is unique. The question is also about the existence. Okay, whether that exists or not. You can use similar techniques from complex analysis to analyze this problem. But at the end of the day, what this means is that there need to be relations among these quantities. So these Zns that are defined for various integers, the Z2 must be expressible in terms of the rest of the guys in a certain way. Z3 must be expressible in the rest of the guys in a certain way, and so on. So there are these constraints that they need to satisfy. Okay. So this is certainly an interesting problem, and we plan to investigate it more. But for now, I will just define it for the states that do admit analytic continuation to be this limit, and we call this the multi. All right.
And you know for sure that this cannot be expressed in terms of entropy, von Neumann entropy of 3 systems, 2 systems, 1 system. I mean, certainly some multi-particle entanglement measures that can express like that.
No, but let me just add this.
But this is not one of those.
But that's good. Good point. That's precisely where I was coming to. The need for multi-partite entanglement. Okay. So sometimes people talk about mutual information, right, as some sort of a tripartite information, perhaps, or this measure I3 as some sort of multi-partite measure. And all these measures are SA plus SB minus SAB or SA, whatever, SABC minus SAB and so on. So all these measures are basically given as a combination of entropies of various parties. And one thinks of them as somehow measuring multi-partite entanglement. But let me just point out a difference between these measures and genuine multi-partite entanglement measures. And this is one of the examples. So let's consider the tripartite state. Let's consider the W state. This is just a state on 3 qubits. Okay. And let's consider a GLZ type state. GLZ types. It is a little different from the standard GLZ state. It is the following. Okay, so I've distributed these coefficients unequally on both sides. Usually it's 1 over square root 2, 1 over square root 2. Now, these two states are quite interesting. Now, if you construct the density matrix of these guys, rho W, okay, so this rho W is on 2 parties, right? So let me trace out the third party. So now this would be rho W on party AB, okay, and similarly rho GLZ prime on party AB. In both cases, I've traced out the parties. Now, if you look at the spectrum of this row and the spectrum of this row, these two spectra are identical. Now, if you trace out B and look at the further reduced density matrix rho A, and similarly here, the spectra of these two are also identical. If you trace out A and look at rho B, and the same thing here, their spectra is also identical. So these are what are called isospectral states. Okay. And as you know, all the bipartite stuff comes from starting with eigenvalues, taking their powers and summing. So when you have such states where the entire spectrum is identical, not only for the global, meaning for this when you trace out one party, but when you trace out other parties also, it could be identical. So in that case, no bipartite measure, not only Neumann entropy, but no any entropy also is going to distinguish these two states. And these measures easily distinguish these states.
So why do you want to distinguish them? Maybe they have the same entanglement.
I just said these distinguish them.
No, I know, but why do you demand that? Maybe they have the same
Want to
entanglement.
prove final things again. This is what you would say is that they have the same bipartite entanglement.
I mean, does it have bipartite entanglement at all if you take the W state? If you reduce over 1, don't you get a density matrix which is the product? No.
Okay.
So can I ask one more thing? One of the reasons you use entropy is of course because it's expensive. I mean, if you just wanted a measure, you could have used, as I was saying, distance to the nearest product state. Distance to nearest product state will always give you a good
But
measure.
you see, I want to measure this holographically. That is my guiding.
But is it extensive? This is extensive in that.
We will see how this changes with the size of the system. Because we will obtain an explicit holographic dual, and there we will be able to see geometry. How geometry controls these quantities. The way Rita can agree surface, you understand that. Log and so on.
I see. But just for qubits, if I take like 10 or 8, like Q traits and Q, it will scale.
But that depends very much on the state.
Yeah, it depends on the state, I suppose. If I take a system of, instead of 1 qubit, I just take identically n qubits,
Okay.
then does it get multiplied with n? I have this 3 system and then maybe I take 3 n systems instead of taking 3 systems.
Yeah.
You
So
just get a
fine.
factor of n.
Maybe this is what you mean. So if the density matrix is a product density matrix, then this guy adds up.
This guy also adds up.
Yeah. Exactly. Yeah, so that's a nice thing. So here I defined this guy for rho AB, right? So I have 3-partite state, I traced out the party C, and I have a density matrix of AB, from which I constructed this measure. Okay? Now, if it were so that this guy is just rho A tensor rho A, you just happen to factorize, kind of goes towards one of your questions. Then what happens is that this, there is no talking between A and B, so this wiggly stuff just comes out, okay, and this stuff just goes in. So you have a bunch of horizontal lines and a bunch of vertical lines, and each horizontal line gives you the radiant of rho A. This guy will also give you that, right? So what you will get is trace rho A to the n whole to the power n times trace rho B to the n whole to the power n, and then you can do this log of this and 1 over 1 minus n. So because of the log, this n just goes down and then adds up.
Is there a similar simplification if you have an A-B state?
No, this is much more complicated.
If rho AB, for example, is maximally mixed. If rho AB proportional to identity,
Rho B is proportional. Yeah, then you can do it. Then you can compute.
then it is easy, right?
Then it's easy.
So for maximally, at least for the tripartite case, the maximally entangled
Yeah.
is.
No, but the point is the absolutely maximally entangled state for multiple parties can have
It
very
is
rich
much
structure.
harder. Yeah.
It's not just yeah.
So in the end, this is the definition in terms of the density matrix of 2 after you have traced out 1.
Yes.
And if you had n parties and you
Q parties, let's say Q parties, because we have the number of replicas.
if you
Yes.
had q parties, then you trace out 1 and still use hyperlattice.
Hyperlattice.
I see. So this works even if your initial state was mixed.
Yes, because it's defined for density matrices. Yes. But the questions of separability, I don't want to answer.
I know. Yes.
This whole different one.
Right.
Okay. All right. And exactly, this is deceptively. I mean, it is not manifestly symmetric in all the Q parties. But if you think about it a little bit, you will see that it is indeed symmetric in all the Q parties. Here I broke the symmetry by tracing out, let's say, party 3. Right? But if you restore that and see what this measure is in terms of sine psi bar, you will actually see that it's a diamond lattice. And then it's symmetric for the three-dimensional one. Okay. Okay. All right. Yeah. So another point that I want to make is that let's say how for finite systems, for let's say a bunch of qubits. So let's say I have a state of 3 qubits, a general state. Here I give some examples. Let's say there is a general state. Now, can I compute this quantity? Well, one thing is that first of all, this guy needs to be analytic. But let's say not this quantity, but how about this quantity? Can I compute them efficiently? Not really, because this is a problem of n by n lattice with some particular vertex. So it's a vertex model. You have statistical mechanics where each vertex is specified by the density matrix that the state has. That's your vertex weight or Boltzmann weight, sometimes called. And then this guy's size is n. It's a square lattice with n by n. So it's clear that I should not be able to compute this easily because that's like solving statistical mechanics completely. Okay. Usually in statistical mechanics, one is interested in some n going to infinity limit, but here we are interested in some n going to 1 limit. So it's a bit different from that. But even the individual things, you need to put it on a computer. And so far, for example, we have been able to get. So you can sometimes try to use integrability techniques. So for W state, and integrability techniques work. And then you can write this down in a closed form, in a reasonably reasonable form. But for general states which are no integrability, which do not have any integrability, then you really have to put it in the computer and calculate this by brute force. So in that sense, it's a measure that is a bit difficult to compute for qubits, but as I will argue for holographic states, it has a very nice description. Okay.
So it also has a nice path integral description.
Yes, I'll just start.
That's why it has a nice description holographically, I guess.
Path integral description meaning the.
In a quantum field theory, because you're just gluing. I mean, you're cutting.
Yeah, but all the measures that I described with the permutation elements. This is one such measure, right? This is one of those measures.
Yes.
But also all the measures when specified with permutation elements have a direct description in terms of twist operators, where you just use the twist operators of those permutation levels. Okay. So in that sense, all those measures have a nice quantum field theory description in terms of correlations and twist operators. The point is, when a quantum field theory is a CFT with large central charge, can you make more progress? Okay. So now let's.
What's the answer?
What was
I shrugged.
You just start. Okay. So now let's compute this in CFTs. So we will now take a particular example, let's say of a three-partite state, Z3, n. Okay, so this is a three-partite closed state with n replicas. Sorry, n square replicas, because you had n by n, so there is n square replicas. So the way this is done is that, so let me actually first review the bipartite cases a little bit so that the language will be there, which will let me address the tripartite case in simple fashion. So let's say you have this lower half plane and an upper half plane, and this is part A, and this is the part A bar, the rest. So what you do is you construct the density matrix by doing these things. So this I prepared, the state is being prepared by some immediate path integral. I'm just looking at a particular time slice. I will not say what this is here. So once I do the rest of the A bar part, I get a cut plane like so, right? And then the idea is that you have a bunch of these, and then you do one after the other. So you are now doing this guy with this guy, and this guy with this guy. So this gives you a ramified manifold, which basically looks like, let's say in a vacuum state, a sphere with two branch points, where it's, as you go around, you come back to the same point after 3 rotations in this case. Okay, but in general it could be n rotations. Okay, so there are 2 branch points like that. And the Zn replica symmetry is the one that takes you from one sheet to the other. Okay. So you can think of this as insertion of 2 twist operators, and then this entropy is basically correlation function of the twist operators. And the way one could think of this holographically is as follows: you take this sphere with a cut, and you unfold this to some other boundary, which would have higher genus. So for now I'm just restricting myself to 2 dimensions, but you could do this in higher dimensions as well. So just so that it's easier to see. So you take the sphere, you unfold this into a higher genus surface, okay, and then the way Mandelstam argue for this is that the boundary enjoys the replica symmetry, the Zn replica symmetry. So let us assume that the dominant bulk saddle also has a Zn replica symmetry. Okay. So you have this bulk geometry which has Zn replica symmetry, and then the idea would be then to orbifold this bulk geometry by this Zn group. Okay, so sorry. So there is some replicated manifold, and there is some Zn symmetry, and this is a particular 4-dimensional locus of Zn fixed points. Okay, the bulk geometry to begin with is a smooth geometry because the solution lies in this equation with this replicated manifold as a boundary condition. And once you orbifold this, you develop a conical singularity at the locus of Zn fixed points. Okay. So as a result, what you obtain is that you have this this boundary. I should also say that when you orbifold, your replicated boundary comes back to the original boundary. So I'm drawing this original boundary here, and from these two Zn fixed points shoots out a locus, the co-dimensional two locus of the Zn fixed points, and in the bulk it can do whatever it wants to do. Okay, and because this is also Zn fixed point, this is also Zn fixed point, so they connect like so, and then the idea is to compute the correlation function of the partition function of this CFT using holographic methods, where you just compute the action of a gravitational solution that describes this geometry with a conical singularity. This conical singularity, because this is coming from the Zn orbifold of a point which is smooth, it has a 2 pi by n opening angle. So this is the conical singularity with 2 pi by n opening angle. So that's the picture you have. So a gravitational action on this solution will give you the nth radian. So the way to make progress, I mean there are many ways, but one way is to notice that such a geometry can also be engineered if you had a cosmic brane that is supported on this conical singularity. A cosmic brane of some particular tension, I think some tension like that. So So what I'm doing is that through the gravitational action, I'm adding a matter source with this particular action. Okay, and then the idea is to solve the equations of motion for the brane and the gravity together, and evaluate only the gravitational action and not the brane action, because the brane was not there to begin with. You just put it in by hand so as to engineer the geometry that you're interested in. So you're only supposed to evaluate the gravitational action in the presence of this brane. Okay. Now this problem in general is also difficult to solve for general N, as I was saying, because this is a heavy cosmic brane with action of the order of 1 over g Newton. So what the case where you can make progress is when you take n close to 1. When you take n close to 1, this coefficient goes to 0, and this becomes a very light brane, and it does not backreact in the geometry. And you can simply compute the gravitational action using, solving the equations is relatively easy now, because you don't have to solve the gravitational equations, because this does not backreact. It's the same solution that you started off with. It's just that you have to solve the equations of motion coming from this brane action, and the action is simply the area term. So you just have to minimize the area, and you get the minimal surface as a solution to the equation of motion for the brane. Okay, and because the entire solution is a solution to the equation of motion, instead of computing variation of the gravitational action here 1, you can also compute the variation of the brane action here 1. Both are identical, and this is what gives you the one entropy is equal to area over 4G. Okay, so this is just the review of Joburg's Mandelstam method, which shows that, which basically proves the Ritha-Kanagi formula from the mathematics. Okay, so we would like to do a similar type of trick for our measure. So in that case, we have, I will work with Z3n. So I have 3 regions, A, B, C, and all of these are glued according to the replica, according to the measure that was specified. So so let me do it this way. So these are the 3 replicas, but I need to repeat this 3 times here. It's a bit difficult to do it here, but let's try. So what we are doing is, first of all, we are gluing this guy directly with identity. So here also I have this power. I'm just not drawing it, and this guy also. So the first party has been glued with an identity map, and the second one, this guy glues here. So it glues like this. This kind of glues here. Same thing on these sides. And then the third gluing of this party is to this guy here. So this guy and so on. So this is just, I'm just drawing the same picture that I had in terms of the density matrix for the actual CFT geometry. Okay.
So actually there's pictures I think you confused, but just to understand, so you're working with Q equal to 3.
I'm working with,
There's pictures for Q equal to 3, right?
yes.
So if you have Q equal to 3, the boundary replica manifold is clear. You cut it and you glue it in the right way according to this
Yeah.
n hyperlattice whatever.
Yes.
In this case, it's just n cross n, so it's not a hyperlattice, just a square lattice.
Yes, square lines.
I see. And now you're looking for a bulk solution
Yes.
subject to those boundary conditions.
Subject to this boundary.
I see. Now I've not understood. Like you're about to tell us that it's a conical singularity or not a conical.
It is going to be able
It will
to
still be a conical.
yeah, exactly. Exactly. So let's see how it looks in the ramified picture. So you have this plane, right? From that plane up where the CFT lives. Yes.
Compared to the picture you had before, just
Yeah.
so I understand, the pair that connects the leftmost interval
Yes.
is the one that you did not draw before, right? In the grid.
Yes.
It's the one
That
that
was
was
the idea,
erased.
yeah.
It's the dotted line.
Exactly.
But otherwise, the second one is the one that went to the left, and then the one.
Yes. Exactly. That's exactly right. Okay, so in the ramified picture, so you have a bunch of these stacks, right? Stacks of planes with these 3 cuts. Well, I mean, this cut is at infinity. So you have these 2 cuts, and there is one other cut at another branch point at infinity. And what is happening is that there are multiple stacks. So there are 9 stacks because there are 9 replicas. So let's look at what is happening here near this point. So as you go across this point, you land on another sheet. Okay. Let's look. I just want to draw a local picture first of this point. So as you go across, you land on this strip, on this sheet, on this sheet, and on this sheet. Okay, and then you go back again onto this sheet. Okay. The same thing happens here. So first of all, there are 9 sheets. So I'm just taking an example of n equal to 3. So I have 3 times 3, 9 sheets. So there are sheets like that also. Okay, so here also these 3 sheets, you go like this and go back. Okay, this is what happens if you go across this point. The first 3 sheets go into themselves as you go around. The second set of 3 sheets go into themselves as we go around, and the same thing happens here. Okay, now here locally it looks the same. As you go around, you enter another sheet, but not this sheet. You go to this sheet. Okay. then you go to the top sheet here, and then you go back. Okay, so the Z3 does act on both sides, but these two Z3s are different. Okay, so on this next sheet, if you do that, this will give you go to the second sheet here, second sheet of the second set, and then the second sheet of the third set, and then it takes you back. So both actions are Z3, but they act a little differently. They mix each other up. So now we will do the same thing. We will take this rectified geometry and fold it and find a bulk solution to these boundary conditions. And following Likovitz-Martasana, we will assume that the bulk solution also respects this Zn times Zn replica symmetry. Okay. And
Before I go to the bulk, on the boundary, can you make progress in this geometry for a CFT2?
we can do what?
Can you understand this from a
Yes.
CFT2 point of view?
Yes, we can. Yes, we can.
And also
So-
higher CFT or no? CFT.
Higher dimensions?
Yes.
Higher
That's
dimensions?
something harder.
No.
CFT2, you can understand this
This
structure.
reduces, exactly. You can just do this calculation purely in CFT2. Because this gives you a correlation function of very specific type twist operators, and then that can be.
And the final answer is then to do, it depends sensitive under theory, not just in the central charge or some such thing.
No, it does depend. There's a lot of universality in the final answer. Okay, the reason is the following: that let's say you are interested in case of 4 intervals. In that case, it will give you a 4-point function of the twist operators. Okay. And then for large CFTs with large central charge, you can show that this correlation must be dominated by the leading conformal block.
By the identity block. By the identity block.
Not by the identity
No.
block. No, because that's exactly the difference between this and the Ryu-Takagi stuff. Because in the Ryu-Takagi stuff, this guy, this twist operator and this twist operators, they are inverses of each other. If you collide them,
Yeah, exactly.
they give you identity.
Yeah.
But that's not the case here.
Yeah.
It's this times this is what is identity. At infinity is also there is another branch point. So there are 3 mark points, or 4, however many. So the algebra has to be that this times this times this times this time, all of them, when multiply, they give you 1. So just with this, which are going to collide, whose OP you are computing, does not by itself go to 1. It gives you some other permutation. So the leading operator there has to be a twist operator in that sector.
Good. So some of the dimensions of these twist operators are perhaps important.
Exactly. So only the twist,
Finance.
only the dimension. But that, it just depends on the conjugacy class of the permutation associated with the twist operator. And what the permutation is, I have already fixed that. So in that sense, it's quite universal.
And if you have a free boson or a free fermion, is there a nice answer you get for this?
Yeah. I think even in general dimensions, for free theories, one can probably compute.
Does it have some area law kind of? Does it have some analog of?
No, this I haven't done. I mean, in the free theory, I haven't calculated. That's a good question. Okay, so let's look at a particular time slice of the bulk. So what I've done is that I've considered this bulk geometry. I've assumed that the bulk geometry preserves the replica symmetry, and I orthofold this bulk geometry by the replica symmetry, which is Zn times Zn. Now what does that do? So there are 3 mark points. As I said, after orthofolding, the boundary goes back to what it was. It is not replicated anymore. And now there are singular loci associated to the fixed points of the replica code. Okay, and what are those fixed points? Well, we saw this is a fixed point of a Zn. This is a fixed point of another Zn. And the one at infinity is also a fixed point with respect to the diagonal combination of the 2 Zns. Okay, because as I said, this times the other guy has to be 1. So the other guy is just the product of these 2, and it's inverse. Okay. So you get a bunch of loci which are fixed under Zn replica symmetry. So for example, the loci that shoot out from here they shoot out from this point, and this point, because there are really 3 points, 3 fixed points here. This stack is disconnected from this stack, is disconnected from this stack. Okay? So you will shoot out 3 loci of so again I'm in back to n equal to 3 of Zn symmetry, or n loci in terms of Zn symmetry. Similarly, you will have n loci here of Zn symmetry. So this feature was not present in the Djokovic-Mandelstam argument. There you just had one particular locus shooting out, but you have multiple loci shooting because there are actually multiple stacks, multiple fixed points. Okay, and then similarly, these guys shoot out. Now, there could also be points which are invariant under both Zns. And what happens at those points? So, okay, I should say what I'm drawing here is the drawing for. Sorry for going back and forth. But, so first, let's draw the picture for replicated boundary. Okay. So I have this boundary which when I unfold, I get 3 copies of this point, and I have marked these points here. Similarly, for this point, there are 3 points. Here I have not yet done the unfolding. Okay. So there are 9 marked points on this boundary, and each of them shoots out these Zn fixed points of Zn. There are loci of Zn fixed points that emanate from here, because this point itself was fixed under the action of Zn, as is clear from here. Is this clear?
Sorry, the boundary is now what exactly?
Okay, so this boundary is this stacked manifold, okay, which is glued in a certain way. And when you unfold this, what you see is that this point has 3 images. Okay, so this one. So all this has the same point, because this is ramified. All this has the same point. So this point has 3 images, and I'm just drawing those 3 images. Similarly, this point has these 3 images, and this point has the 3 images. Okay, and now my orbifold. And when I orbifold by first Zn, let's say the Zn that permutes these guys, what happens is that these guys, they become identified. And you get a picture where from this, all these collapse to one image. Okay, and the Zn that permutes this is exactly the Zn that acts like this for these Zns, for these points. So when you orbifold by that, you get conical singularities. Okay, so these guys, because there could be points that are invariant under both Zns, they meet up in the bulk like this. And at this locus, it is invariant under both Zn symmetries. And when you orbifold, these 3 loci, they collapse into a single locus, and these 3 loci, they become conical defects. Okay, and similarly here. And now when you do the remaining orbifold of the other Zn, these conical loci, they combine into a single conical locus, and this, where this was a angle 2 pi, this gets conical singularity. So at the end of the day, what happens is that you get 3 conical singularities meeting each other like so in the bulk. Okay, so each of these guys has a 2 pi by n opening angle, and they meet here just by the virtue of algebra permutation. And we do the same trick as before. What we are instructed to do now is to find the action of the gravitational solution that has this particular singularity structure. And as we said, the singularity is basically a singularity of opening angle 2 pi by n, conical opening angle 2 pi by n. So we engineer this by cosmic brane of certain tension as before. And in general, we will not be able to solve the problem, but if we are going to one limit, this cosmic brane becomes very light. And what we get is that this multi-entropy is then given by, so the bipartite entropy was in the case of CFT2, it was just this length of this minimal area surface In this case, it was just the length of this geodesic, but now it would be the length of this particular geodesic network, where what you are instructed to do is to minimize the area, or in this case length, of all these segments, the sum of all these areas. So in particular, this is also, you have to find this point of intersection and minimize the total length. So this is what we claim to be the multi-entropy.
Abhijit, is there somewhat favor of Renai entropy of a reservoir connected to gravity? Because in the West Coast models, there are similar contributions that come when you compute Renai entropy and is wedge-like configurations.
I see.
Where you have this cosmic brain in the bulk, these which become islands essentially.
Yeah, I'm not sure whether this is related, but we can talk more.
Maybe you can finish the next 5 minutes or so.
Yeah, sure. On this one. So I will just say a few words about higher dimension generalization. So as I was saying to Finn, that for CFD2 you can make progress purely in terms of conformal field theory, where you think of these things as correlation function of twist operators and compute these correlation functions in a large C approximation, and you can see that they agree with the answers that you obtain from this description. If you had a 4-partite entanglement, you will exactly the same process will give you a geodesic network of this type, and what you're supposed to do is you have to minimize the length of all these geodesics and so on. Okay, so in the 2-dimensional case, you can do a check of this description. But the nice thing about thinking about this from a geometric point of view is that you know what the answer is in higher dimensions. In higher dimensions, let's say in the bipartite case, this is a particular time slice which is a sphere, and the bipartite case, let's say this is the area, this is the particular region of the boundary that I'm interested in computing the entropy of, and it is given by this Ryuta-Gravity surface that extends into the bulk. But now in the case of multi-entropy, you would have multiple types of areas. So you will have, let's say this is a sphere, and then there is some region near the south pole, some region near the north pole, and some region near the equator, and you want to compute the tripartite multi-entropy of these 3 regions, and then what the dual that you get is the following: is basically some sort of a soap film that stretches, that is anchored on the boundaries of these guys, and it is not. So if it were just this would be what we call the connected entanglement wedge corresponding to these 2 regions. But because these 2 regions are also counted differently, you also have a soap film that stretches in the middle. So you have a soap. So the prescription is basically that the multi-entropy is given by a soap film that is anchored on the boundaries of regions of interest, such that all the regions are separated by one of the soap films. They are not connected. Okay, so this is the holographic dual for the multi-entropy in general. Okay, so I'll stop here. Thank you.
The geodesic diagrams you wrote there, both for 3 and 4, looks awfully like written diagrams.
Yes.
Any way that I can think about these soap bubbles as somehow fattened written diagrams?
Yeah.
Integrating or minimizing over the bulk. Why do you say written diagram? Written diagram will integrate over the bulk.
Yeah.
So you're minimizing it.
Yeah, it's not exactly like written diagrams, but they look like it. Yes, that's true. Yeah, I'm not sure. I mean, maybe there is a way of thinking about the correlation function of exposure.
Yeah, but it's minimizing, right? You just minimize
Yeah.
at that point. So you don't, there's no integral.
But if the operator is heavy, you have the geodesic approximation. In that case, the preferred path will localize. It's true, the full
The
formula.
written
is
diagrams
integral,
reduced to
but-
geodesics.
Can you comment on why the case with the 2 periodicities being different doesn't work?
Okay. Yes. So what is important here is that you have a Zn and a Zn. So let's say the generator of the first Zn is G1 and the generator of the second Zn is G2. Then the subgroup generated by the product, G1 times G2, which is the twist operator that lives at the other side, is also Zn. If it were Zm and Zn, then that would be the least common multiple of the Z of least common multiple of Mn. And then this orthophonic picture will not work.
So in other words, the last set of conical deficits will not collapse to 1.
Yes.
So, so in the bipartite case, there's also this nice matching between the eternal black hole and its the black hole entropy and the entanglement entropy of the thermal field double. Is there in this case for multi-partite like some multi-boundary wormhole that also can similarly?
Yeah, sure. So in this, you can indeed compute these multi-entropies for multi-boundary wormholes, and they would have this type of picture. So in the case of, let's say, a black hole, you can think of this as the area of the Arctic surface. In the case of multi-boundary wormholes, you would have multiple boundaries. And then it's a trisection that you go through here. And the area of this would be the multi-entropy.
Okay, let's thank Abhijit.